everybody welcome. Can you hear me? We better get started now because I can guarantee you Bob's going to need every second of the an hour and a half. It is my pleasure to welcome Bob Budnitz to be our distinguished speaker, and he fully lives up to the title of distinguished speaker, I guarantee it. Bob received his PhD from Harvard in 1968. Before that, he was undergraduate at Yale, both in physics, experimental physics. Then he came here to Lawrence Berkeley Laboratory shortly after that in 1968 and started as a postdoc in the physics division. Well, soon after that, somebody decided, Andy Sessler and Jack Hollander decided to focus on environmental and energy issues at Lawrence Berkeley Laboratory. And so they eventually started this new division called Energy Environment, the former Energy EETD, of course, in which Bob was interested in. He was actually part of the Alvarez group when he first came here. And so he was lured over to that group, and he stayed here until 1978, finally leaving after Jack left. He was the acting director for 3 years. At that time, Bob was called to Washington to serve as the head of NRC's some $200 million a year, which was real money in those times, research project for the Nuclear Regulatory Commission. Then in 1980, Bob started his consulting business in nuclear engineering, safety, and design, which ran for over 20 years. It's still running today. 20 plus years later, Bob joined some obscure laboratory by the name of Lawrence Livermore out in the valley there to work on Lawrence Livermore's nuclear waste disposal program, and again went to Washington and served as the head of their science and technology program, the Office of Civilian Radioactive Waste Management, which he's been called to Washington several times, as you will note. In 2007, we finally lured Bob back here to LBL, where he has developed a very active program in nuclear design, nuclear reactor safety and design for seismic purposes. However, since the subject topic today, a thing of note, is the Japanese earthquake and the tsunami and the effect on the nuclear reactor that Bob's going to talk about, Bob has also been heavily involved with it on Dr. Chu's, the Secretary's advisory panel, science advisory panel, a very small select group that reports to the President. And he's been heavily involved with that, so I can't think of anybody better to be talking about this topic today, and nor could probably Dr. Chu. It's a very important topic because this committee is probably determining the fate of nuclear energy in the United States and the future of it, of which direction to go, not only the United States, but the world itself. So please join me in welcoming Bob to address this in this very important issue, but he wanted me to say that the most important thing, he did not want to be left out, that he is an avid Boston fan and Bruin fan as well. And they're very happy in Boston because the Bruins just won the Stanley Cup, of course, and then Boston finally won a World Series, of course. So anyway, join me in welcoming Bob to this talk.
I've tried to figure out how to turn this on. Is it on? Okay. Yeah, how about those Bruins? And if you don't understand, I wear a Red Sox hat basically all the time, and I'm proud of it. This talk is, as it says, going to talk about what happened at Fukushima and also its implications and what it means for the future. I can't predict the future any more than anybody else, but I'm going to try to tell you what I think it means for the future of reactor safety, and what it means for the long-term future of the nuclear program is very hard to tell. I'm going to try to do this in less than an hour. The time slot goes till noon. It's only 10:30. And so there's time for questions and answers, and I'm sure there will be at least one. But I'm telling you that at 12 noon, I'm walking out that door because I've got an airplane to catch not too much later, going back to the big American Nuclear Society annual meeting in Miami next week, and then a month's vacation. So let me start by giving you some background about nuclear power in Japan, and what I think to do that. Oh, I don't have to turn around. It's in front of me. Japan has nuclear power plants all over their islands. It generates not quite half of all the electricity in Japan. You can see that there are about 20 sites, and they have about 50 reactor units. But there's a concentration of units north of Tokyo on the East Coast, where you see a bunch of red dots, and of course that bullseye there is where the earthquake was. The Japanese rely on nuclear power heavily because a decision they made a long, long time ago. They don't have fossil fuels, and therefore they have to import energy. And what that meant was importing fossil fuels. And so they made a decision a long, long time ago that nuclear power was going to be a central part of the mix of generating electricity there. They've stuck by that. They've in history done a very good job of running their plants. Everybody that's ever gone there has always said, gee, they do a good job running their plants. And we are really caught by surprise by this accident, because who would have thought it would have happened in a place like Japan, of all places? But I'm going to tell you that the accident has revealed some fundamental flaws in the way they were running their things. And I'm also going to try to explain towards the end what I think about what that accident has to tell us about our plants. So let me just start. There are 14 nuclear power plants along the coastline that was affected by the tsunami, and you can see them here. The plant that had the accident is called Fukushima 1. It has 6 units. They're all boiling water reactors. The original design was by General Electric, but afterwards the Japanese Toshiba and Tokyo Electric Power designed similar plants. So they're basically a GE design. And just a few miles south of Fukushima, the plant that had the accident, is another site, Fukushima 2, that has 4 more reactors. They're basically 10. They're different sizes, but they're very close to identical. There are 3 more further to the north and 1 further to the south, and all 14 of those are along the coastline affected by the tsunami. All 4 of them, altogether you can add up the megawatts. It turns out that this section of Japan, this section of the nuclear program generates about a tenth of the electricity in Japan, and they're all down. But some other units have been down too, and they're short about 15%. A little more, which is going to be a really difficult thing for the economy, and of course with the summer coming it's going to be even more short. I'll come to that later. Here's a picture of the plant site in the happier times. There are 6 units, 4 of them along the bottom here. I'll just point. 4 of them here. 1, 2, 3, 4. They may not look like big buildings, but they are really big buildings. You'll see how big they are when I show you a picture later of what's inside one of them. And then there are 2 more units on the other side. It was the 4 units, 1, 2, 3, and 4, that had the terrible accident. The other units, 5 and 6, didn't suffer an accident. And all the reactors generate spent fuel. A lot of the spent fuel is inside the reactor buildings. I'll show you that later. But they have a common spent fuel pool where they move a whole lot of the spent fuel out of the units to this common pool, and you can see where it is there. And so this site is right along the shore, as you can see. Oops, I've got to go the other way. Now, this is the same picture, just showing what the status was. When the earthquake and the tsunami came, 3 of the units were in outages. These were planned. They do refueling outages. Unit 4 was in a particularly long outage because they removed all the fuel from Unit 4's reactor. We'll come to that later and understand how important that was. Because they were, 30 plus years later, they were rebuilding the core support inside the vessel in order to make it renewed so it could run for a whole lot longer. So there was no fuel inside Unit 4. There was fuel inside Units 5 and 6, but they were shut down. And the Units 1, 2, and 3 were running. They were running at full power. They were running along, and that's important because they were the 3 that suffered this major accident I'm going to tell you about. Unit 4 didn't suffer an accident. Well, there was no fuel in the reactor. It was in the spent fuel pool. So I'm just going to show you a stylized picture of what happened. Ignore the writing. I stole this picture from another place, but this is to show you how the initiating event happened. The initiating event was an earthquake that was about 70 miles offshore. And if you see the picture, this is the tsunami developing. But if you look at the picture, the earthquake broke over 400-kilometer length. 400 kilometers, so 250 miles. A very, very long break. And the magnitude 9 wasn't because the ground motion was so huge, although it was big. It's because over that long length, there's a lot of energy, and magnitude is related to the energy. So it broke over this very long length, And the earthquake there isn't, our earthquakes go like this. Strike slip. Their earthquakes are subduction zone earthquakes. And what happened was one side fell with respect to the other side. Just got to think about it. It fell. And the distance that it fell was some tens of meters, or nearly 100 feet in the middle. Over the 400-kilometer length, it fell different lengths. But if you have this huge fall, and it happened only over very few seconds, it's easy to see. You just do this in your bathtub. You try that, you get a big wave. And, of course, it goes both directions because you understand. So that's just a stylized picture that shows that the wave was 400 kilometers long, and as it started to spread east and west, the next picture shows that as it approached the land, and of course the other wave is going the other direction towards, east towards America, but by the time it got here it wasn't much. But this tsunami, which was the approximate cause of all the trouble, was a huge, huge tsunami. Next picture. Most people don't understand tsunamis, and so I put this up because this is perhaps the most famous visual picture of a big wave that many people have seen. I'm familiar with it, have been. This is one of the most glorious pieces of art in the canon of art. This is not what a tsunami looks like. It doesn't look like this at all. That's a wave. What a tsunami is different than this. And I just drew this by hand just to show. The tsunami produces a wave all right, but it's a mile or two long, and in the middle of the ocean, this is an open ocean, and I'm just pretending it's moving to the right. In the middle of the open ocean, it could be some 10 or, in this case, 20 meters high, and it's moving that way at a couple hundred kilometers per hour. But if there was a little ship on the top of that, you could see it. After all, a ship is as big as 10 meters. But the ship would just ride it out because it's going along, just ride it out. But then all of a sudden it comes to the shore. And it's not a wave like that previous picture. It really is a sea level rise that takes place over a minute or two or three, in which you're on the shore, just sea level rises. And then finally, of course, it goes back. And that takes a few minutes. And if you saw the videos of this event, you understand that. So there was this big sea level rise. And the way sea level rises in tsunamis are dealt with, I'm not an expert on this at all, one deals with the height of the tsunami and also how far the run-up goes inland. This one went inland, depending on where you were along that 400-kilometer stretch, it went inland a mile or two or three, and where it struck the reactor, it was 46 feet high. So here's a picture just to show you, it's real stylized, but the sea level's down here, and that's 40. This was actually before details were known. This was put together early on. It says more than 10 meters. It was actually 14. It rose up, completely swamped a 10-meter barrier, just completely went right over it, went over here, and actually the water went around all the buildings to the height of several meters above the grade up here, which is way above this. Completely swamped everything. And as I said, it was a gradual rise. The water was there for a few minutes before it finally subsided and went back out. And during that time, it swamped everything, and that was the cause of the accident. Now, let me go on and just show one more slide about tsunami run-up heights. This is the north of Japan. That's Hokkaido up to the north and the north part of Honshu. And this is going from north to south. That's latitude. That's a great distance, 10 degrees of latitude. And on the right, it shows tsunami heights. And you can see that there are places where the tsunami height is 35 meters and up, 100 feet. At this plant, it was 14 meters. It's in here somewhere. This is where the plant is, in here. And that 14 meters, it has a lot to do with the topography and the coastline and how it's shaped and the run and the slope of the shore and so on. But you can see that there's a huge section of Japan where it was 30 and up meters. 75, 100 feet up. Next slide, and then I'm going to go on to the reactor. This is a picture. It's all in Japanese. I can't read it, but it was explained to me. Along the bottom are different north to south locations on that whole coast. And the red big things are the height of the tsunami. The things down below are different. There's X's and O's and different stuff like that. These are different tsunami walls. All along the coast, they built tsunami protection. They knew about it. Some of the tsunami protection was 5 or 6 meters, some was 10. Some was even 15 meters. So they knew it was coming, but everywhere along that coast they underestimated what they got. You can see it. Not everywhere, but just about. So we're talking about 250 miles of coast that was swamped by a tsunami, in every case larger than they expected. It wasn't just the nuclear plant that got clobbered. Villages and towns, a few small cities, industries, ports, you name it, was all overcome because they completely failed to estimate properly how big that was going to be or protect themselves against it. We in the nuclear industry are puzzled by that. We don't understand it at all. If you look at the historical record in retrospect, since the Japanese started keeping records, which is about 2,000 years ago, there have been 3 big tsunamis like this, 3 of them that were higher than the wall they built in front of that reactor. One in the year 869, one in the 15th century, can't remember exactly. Anyway, there were 3 of them. And we don't understand why they only afforded protection for something that comes around every few hundred years. That really is a puzzle to us, and it is the proximate cause of the accident. Let me just say one more thing before I go on and tell you about the reactor. If you're an earthquake engineer, as sad as this terrible thing is, it's a triumph for earthquake engineering. As best anybody can tell, except that the earthquake knocked out the grid, because the grid is very fragile all over, not just in Japan, but here. Except for that, as best anybody can tell, everything at the reactor rode out the earthquake fine, and it was the largest earthquake that Japan had experienced in its 2,000 years. Now, of course, they didn't have instruments in those days, but there are ways of conferring these things, and nothing as big as this, in terms of the size and extent of it, had struck this area in the 2,000 years that the Japanese have records for. So it was a huge earthquake. The design rode it out. The 6 units, when the earthquake came, the control rods went in, the chain reaction shut down, the power, they lost the grid. The on-site power came on, all the pumps started, things that we're supposed to do did. And then 45 minutes later, the tsunami came and wiped them out. There's also that second plant with 4 units just a few miles down the coast. It also saw that great big earthquake. And it also rode out the big earthquake and shut down fine. It didn't have the tsunami, and it's fine. So I just want to emphasize, it wasn't the earthquake. If you're a seismic person, you're proud of how well that did, and the seismic people don't feel as if there's anything they have to do to upgrade the safety of those plants. And in fact, I was at Diablo Canyon just earlier this week for 2 days. I chair a State of California review committee that reviews Diablo, and they too feel as if their seismic design is as robust as it needs to be, and that's a comforting thing. You ought to know that the earthquake that occurred there was just slightly higher than the earthquake to which they were designed. It wasn't that the earthquake was huge compared to what they were designed for. It was just slightly bigger. And of course, the seismic design has margin, and a lot of margin, which is nice to know. And so they're feeling that they don't think that they have a real seismic design problem there. So what was the problem? The first problem is what I said. You can see it yourself. They shouldn't have put it there, or they should have had a bigger wall. Yeah? I mean, it's easy in retrospect. And when you say this, you have to realize that there are 26,000 Japanese who died in this. 26, not the reactor, tsunami. 26,000 of them. More than a third of them were swept to sea and haven't been found. The rest, they're on the land. But 440,000 evacuated, and their lives were saved that would have been trapped. So the evacuation worked for 95% of all of them, but a little more than 5% of them it didn't work for. And if you look at the circumstances where that happened, it's really, it's tragic as it can be, but in 40 minutes, and even less than that in some cases with a warning, trying to get all those people out of there, they actually did a remarkable job, but they didn't get them all. And 26,000 are dead from that. Finally, you should know, before I get into this, that as best anybody can tell, there was no one was killed by the radiation, workers or anybody else. There are several workers that have radiation doses that are above limits, and 2 workers that actually had quite dangerous doses. And everybody feels bad for that. I mean, it's just terrible. But in fact, the radiation didn't cause, and we'll see about it later, didn't cause a lot of doses. And the reason for that is that the Japanese promptly had an evacuation plan. They evacuated out to 20 kilometers. a little more. It ended up in some areas being 30. And because they evacuated, and they're still evacuated, no one got any radiation from the reactor in the public, as best we can tell. And nobody's got any radiation by drinking water or eating food because they interdicted all that. So it's a huge economic loss, but not a radiation disaster. And the reason for that is because how well the evacuation worked. Now that's, of course, completely different than the Chernobyl accident, which produced a huge, just off-site troubles because the Soviets at the time in Ukraine certainly didn't evacuate anybody for a whole bunch of days. In fact, they didn't tell anybody. During which time, people got very, very large exposures. That didn't happen in Japan. That part worked. But the tragedy, of course, is this reactor accident. I'm going to come to that now and talk the rest of the talk mostly about that. Okay, so I'm going to first describe what a boiling water reactor is and then get into some more details. The boiling water reactor is a very large pot. In fact, you'll see how big it is. It's about 50 feet high, about a dozen feet around, 8 inches of steel. That's when I show the reactor vessel, with 12 foot of fuel in there. And when the control rods are pulled out and the chain reaction starts running, what it does is the heat from the chain reaction boils water. And the boiled water goes directly to a turbine. It's a direct cycle, not like a pressurized water reactor where there's an intermediate loop. That steam goes directly to a turbine. The turbine then comes around, and after the turbine does what it does and generates electricity, the low-pressure steam goes to a condenser where it's condensed, pumped back in the reactor, goes around the loop. Conceptually, it's very simple. It's just, I hate to say it's just a way of making steam. I mean, that's sort of really flip. But in fact, it's a direct cycle steam, and this loop is slightly radioactive with water. Slightly meaning it's not very radioactive, but it's certainly not clean. And that loop, when it's running, just goes around. And these reactors, as you saw, were the smallest. The first one was 400 and something megawatts, and all the rest of them were 700. The sixth of the six was about 1,000 megawatts. So it's a simple feature, and it has a containment structure around it. Next slide. Now, this is the fission process. I won't spend any time with this. If you don't know how this works, I certainly can't explain it here. But uranium is fission, splits in two, or sometimes three, when a slow neutron hits it. The neutron hits it, splits in two. Those blue things are the fission products. It splits into two large nuclei, different ones, depending on which fission. And it produces at least two neutrons, sometimes three. And those red ones are the neutrons. They get slowed down by the water, and then they hit another one, and this is a chain reaction. It's pretty simple to describe. It's a chain reaction in which one neutron fissions, produces two or more. They fission the next one, and as long as the process keeps going, it produces heat, which heats up the water. And of course, it's the hot water that later makes electricity. I won't say much more about that, except just to give you a feeling for what the fuel looks like, because we're going to see a picture of melted fuel in a minute. The fuel is in long rods. They're 12 feet long. They're about as big around as my thumb. Well, not quite that big around, about as big around as that finger. And they're 12 feet long. The outside of them is a zirconium metal cladding. Zirconium is chosen because it has wonderful metallurgical properties. It has good neutron properties, doesn't absorb very much, and it has good thermal properties. So there's a zirconium. It's a long tube, 12 feet long. It's actually a little longer than that. And inside it are the uranium fuel pellets. They look like aspirin tablets, actually a little bigger than that, a little higher. They're these little aspirin tablets going inside that, we call them fuel pellets. There's sort of a stylized picture of it here. And those are a uranium ceramic, okay? Actually a uranium oxide. And they go inside this rod. The fuel assembly is an 8 by 8. Actually, it says 62 because there are a couple of control things, so it's 8 by 8 in an assembly, which looks like that, in a square box. And then there are 500 odd assemblies in this particular reactor. You can see that it's more than 30,000 of these individual fuel rods and in 500 odd assemblies. And they're all held together inside the reactor, which is over on the other side. Now, the reactor vessel is 40 odd feet high. The active fuel is only about 12 feet. And the rest of it is there are control rods coming in from the bottom, and on the top the steam goes out, and there are steam separators and a whole lot of other stuff that I won't go into much here because it's not relevant to what happened. Now this is just a picture of, so you'll see what the scale of this thing is. In the next picture you'll see this is the primary containment Browns Ferry is a reactor just like this. It's a little bigger in size, but it's about the same, in Alabama. And this is under construction in the 70s. And that's just to show you what the scale is. This great big torus I'll talk about in a minute, and then the vessel. And way up on the top there, you can see a gal sitting up there. And I don't know that it's a gal, actually. I can't tell. But why not? And this is just to show you the scale, and that's all inside one of those buildings I showed you. In fact, there's more to it than that, because here's the lid down at the bottom. I showed this picture, just pulled it out to give people like you that aren't familiar a feeling for how big the scale is of these great big devices. Now, here's a stylized picture of it that just shows how the containment works. The pink thing is the reactor vessel with the fuel on the inside, and outside it is something that's called the dry well. It's this thing that looks like an inverted sort of 100-watt light bulb. And it's dry, and the containment, which keeps the radioactivity inside, is this gray thing that goes all the way around, and the containment is concrete, a couple feet of concrete lined by steel. And then down at the bottom here, is this torus. You saw the picture of it going around? It looks like a donut. It's huge. Down at the bottom, it's about half filled with water, and it communicates through some check valves here with this, so that if water got in here or pressure, this big torus is connected to this dry well. The trick in a reactor like this, as in all reactors, the secret of making sure they're safe, is that you've got to keep the fuel in the vessel underwater. When the reactor shuts down, it still generates heat. A 1,000 megawatt electric reactor, which is 3,000 megawatts thermal, if you shut it down, after you shut it down, it's still generating 100 megawatts thermal, which is a lot of megawatts. A few days later, it's still generating 60 or 80 megawatts. So there's a lot of megawatts being generated from, this is decay heat because of the radioactivity, and that's going to melt the fuel unless you keep it underwater. So the key for reactor safety, once you shut the chain reaction down, is making sure that the fuel inside the vessel is underwater. And we're going to come to how that failed, and that's what caused the melting and the release. As long as it's underwater, it'll be safe. There's no release. When you lose the ability to keep water under there, then you get in trouble. Now, this also shows, just in the upper right-hand corner, that there's a spent fuel pool high up in the building. What they do is, every 18 months or so, you shut down to refuel, and in a reactor like this, about a third of the fuel is taken out and new fuel put in. And then they run again, and 18 months later, another third is put in. So a typical fuel rod is in there for about 3 cycles, 4+ years. And the way the spent fuel pool is arranged is because you can shut down, flood the whole thing up, and a crane just takes the fuel out of the top, moves it over to the spent fuel pool, and that pink thing over there is a very stylized, sort of an offloaded core. And at these reactors, units 1, 2, and 3 were the ones that had this terrible accident. Each of them had several cores in the spent fuel pool, but they were all really old. Old meaning nothing, they hadn't been downloaded for a while. And none of those spent fuel pools got in trouble because there isn't very much heat. And although you do have to remove the heat because there's some, there isn't very much heat and the spent fuel pools stay underwater. In fact, the rules in the United States require that in a spent fuel pool like that, there has to be at least 23 feet of freeboard water above the spent fuel. So if you lose cooling, that's a lot of water to boil off before you start getting in trouble. And for the 3 units, 1, 2, and 3, the boil off would take weeks. Unit 4, on the other hand, had the whole new fresh core just 3 months ago, at the accident 3 months ago, offloaded into the spent fuel pool, Unit 4. And I'll come to why that's important in a minute. And there was no fuel in the reactor. At Unit 4, we thought for the longest time, for more than a month, that they had lost level in that spent fuel pool, that they had an explosion because of the hydrogen generation, and it blew the roof off. And now we know that isn't so, and I'm going to come to why that is later. But Unit 4 had a whole fresh core right up there, as well as some older stuff. Let me keep going. So this is another picture of the same, little different. You can see that the steam, the gray thing is the steam, and then the condensed water goes back in, and this is just more of the same. I won't go into this in more detail. I'm going to go on. Now, and here's the refueling configuration. What you do is you take the lid off, you fill it with water, There's a gate that you take out, and then a crane just moves it over while it's underwater. Okay? That's how refueling takes place. Now, this is a picture, just a stylized drawing that I stole from General Electric of a typical one, and you can see what the scale is. Remember that great big thing, the picture I showed you, the little girl on top? That's inside here. That's inside here. There's more above it. This is a great big building. I mean, this is a great big building, many stories high, and the reactor pressure vessel is this red thing, and the reactor fuel itself is inside that. And here's this great big torus, and there are several of these large pipes, about a meter that connect it to what we call the dry well. And the containment is this large structure here that goes around. And that containment is intended to make sure that if radioactivity leaves the vessel, it won't get into the environment. But it did. And here's a picture of a typical spent fuel pool empty, just to show you. By the way, this is big because I told you that there's 23 feet above the fuel. This is about 50 feet deep and about 100 feet on the side. So this is a big pool. Now, here's the normal operating configuration. I just said this before. The red is steam going out to the turbine. The turbine makes electricity. The red is low-pressure steam, gets condensed by the seawater that cools it. Then that red pump pumps it back in, goes back around the loop. That's just the normal operating condition. Okay? Crucially, when you shut down, as happened after the earthquake, when you shut down, there's still quite a lot of megawatts being generated in the middle of this reactor. And those megawatts have to be removed. So the normal operating condition for shutdown is that this same loop works, except that there isn't enough to drive the turbine. So there's a bypass valve, and the steam goes out that red line, bypasses the turbine, goes to the condenser, removes the heat, gets pumped back in, and that loop just is the way that the shutdown reactor normally cools itself. The problem is that steam loop and pumping it back in requires electricity. Electricity on that pump that's labeled in red there has a little electricity sort of logo on it. The electricity there is required for that to work. So here's what happened. The earthquake came along, the rods went in, drill rods, the chain reaction shut down. And this is in all three of those operating units. And they lost the grid. Well, the reactor's designed, when you lose the grid, to generate electricity on site. They had on site, every one of those 6 units had a diesel generator capability. Every one of them had 2 large diesel generators, each of which looks like one of the, I call it choo-choo train when I was a kid, a big train engine. They're huge. They fill this room. Each has 2. There were 12 on the site, and all they needed was 2 or 3 of those to run, and they could have saved everything. But in fact, they started up fine, and everything was working fine. 45 minutes later, the tsunami came, out they went. It's the tsunami that caused the accident. So just remember, the normal loop can only work with electricity. Okay? So here's what happened. When the tsunami came, that regular pumping scheme didn't work because they knocked out all the diesels. Some of the diesels themselves were swamped. They were at a low elevation. But crucially, and this is another flaw in their design, and we don't understand it, if you don't mind my saying, and this is a criticism that we're having of them, right behind the diesels is a switch yard where the diesel's power, and it's 4 kV, 4160, it's 4 kV gets distributed to the plant and it's stepped down, and there's a switch yard there, and that was all swamped by the water. So it all, even if the diesels had worked, the switch yard wasn't going to work. So there was no AC power anywhere. We call that an AC blackout, and ordinarily in a blackout you can restore, but they didn't restore AC power to these units for more than a week in the first case, and even almost 2 weeks by the time they restored enough to do everything. So they were in a blackout situation right away after the tsunami came with no AC power. But reactors designed to run without AC power. Reactors, every reactor in the world is designed so when you have a total blackout, it can still run and put water back in the pot. And here's how it works. There's a steam line that I showed you. The steam line, the reactor is still making steam. Some of the steam is bled off to a turbine-driven pump where the steam drives a turbine, the turbine drives a pump, the pump can put water into the vessel. And the way that works is shown here. This suppression pool, that great big torus that I showed you, is half filled with water. The steam-driven pump, which is in green, takes suction from that, pumps it, puts it back into the line, and fills the vessel, keeps the vessel full of water. But the vessel is boiling. And only some of the steam is driving that pump, only perhaps a tenth of it, by the way. The rest of it is disposed of by going out the top through the relief valves. And the way this reactor is designed in this case is the steam from the residual heat goes out relief valves. It isn't shown here. And it gets brought back down through a pipe into the suppression pool where it is condensed by this very large volume of water. And then it takes suction again, steam goes out, comes down the suppression pool, and it condenses. Now, that'll only work for a certain amount of time. And in fact, it's designed to work for a couple days before ultimately the suppression pool gets so hot that it starts to boil. And boiling water isn't suction for that pump, it just cavitates. So after a while, unless you can restore the rest of the power, this pump is only going to last for a certain period of time before it fails because it doesn't have any suction. In our reactors, that cycle is designed to last for 5 or 6 days before that boil up and cavitation works. In their reactor, at Unit 2, this scheme worked for about 20 hours. And at Unit 3, it worked for about 3 days, about 70 hours. And in each case, what happened was the pump failed because the control systems didn't work, because although it's immune from needing AC power, it needs DC power for controls. The controls and instrumentation for the pumps need DC powers. They have these big battery banks. If you imagine a car battery like we all know and love, a battery bank might have 100 of them gang together. And there are 4 or 5 of those. There's a lot of batteries on site. And every reactor has them. But ultimately, the batteries ran out because of the drawdown of the battery power. And the batteries ran out in one of the units at about 70 hours. At another one, it failed in about 20 hours, and we don't understand why it failed. It should have run for longer. But in Unit 1, they had a different scheme. I can't go into some details, but in every case, this steam-driven system that runs without AC power put water into the vessel, and then it stopped. And as soon as it stopped, the boiling continues, and very shortly thereafter, in the matter of just a couple hours, the water level comes down, and the core gets uncovered, and disaster strikes. And that's what happened in all 3 of those units, one after the other. So the causes: the grid was failed by the earthquake, the tsunami failed the diesels, the system worked for a while. We don't know why it worked not as long as it should have in one of the units, but in the others, they got exhausted. They exhausted battery power. They ran out of control. They couldn't restore it. They desperately tried everything they could to restore it, and they lost injection, and the level came down, and disaster struck. Let me go on. So here's just sort of a stylized picture that shows a kind of I stole this again from somebody. It shows this, that the battery power didn't work, and they lost control, and then they couldn't inject. Now, as soon as that happened, here's what happens. You get level comes down. And because the decay heat is so intense, when it's not underwater, to be able to take heat away, very quickly the part of the fuel that isn't underwater heats up, and the first thing that goes is the zirconium cladding on the outside. Zirconium is a wonderful metal, but it undergoes the following reaction in the presence of steam. Zirconium metal plus water, and that water is steam, oxidizes to an oxide and releases hydrogen. It's a very simple reaction. It starts in about 1200 degrees C, which is hot, but that happens rather quickly when it's uncovered. And it's exothermic, meaning once it starts, it heats up the next one, and you can't stop it easily without a whole lot of water and a whole lot of heat removal. So as soon as it starts, it really just goes very fastly, and it's exothermic. Okay? And here's then what happened. So the cladding melted. The part of the cladding that didn't oxidize melted. The steel structures around it melted. At a certain point, the fuel rods break up, and they all fell to the bottom. There's sort of this debris bed. And then ultimately, because of the lack of water, At a certain point, which is 2,700 degrees C, that's really hot, you start getting melting of that uranium, the uranium fuel pellets. And you end up at the bottom with a bed of rubble. I think I've got it in the next slide. This is a typical sort of stylized picture of a bed of debris, just this rubble at the bottom. And this is really hard to cool. The danger in this situation is that, in fact, this stuff is going to melt through the vessel and then get outside. Although in each of these three, almost all that stuff's still in the vessel, which is nice to say, but not all of it. And there's a typical sort of a molten pool. After a while, if it gets really hot, it'll become molten rather than this rubble bed. And that's hotter still, although it's hard to maintain this because a molten thing is easier to cool. So let me go back. I'm going to go back up here. Because I want to show you a picture about where the radioactivity emerged. And this is, I have to do it from this drawing at least. I should have put another one in, but here it is. What happened was, the steam is going around, coming down through these valves to the torus. The torus is heating up and finally gets to the stage where it doesn't have heat exchange properties anymore. And then the level comes down and hydrogen gas starts going out the same roof, comes down into this torus, which, by the way, is connected to this very large containment. Now, as soon as this starts happening, the radioactive gases in the core, the gases, which are a few percent of the radioactivity, escape with it. And some of them are noble gases, and some of them are non-condensable other gases, and some of them are things like cesium oxide, which are very dangerous, but they're gases. The gases go down, and they fill this, they start filling that and overpressuring it. At a certain point, they overpressure, it's connected, and they overpressure this light bulb thing, which is the containment. Now, the containments in all these reactors are actually filled not with air, but with nitrogen, which is an inert gas, to make sure that when this happens, all of our reactors like this have this, make sure that when this happens, the hydrogen won't ignite, because it's nitrogen. There's no air. It's a safety measure. But what happened was that light bulb finally got to be too much pressure as this accident evolved, way more pressure than it could stand, and the crew wanted to relieve the pressure and release radioactivity to the environment. They ultimately did that. They released radioactivity out to relieve this. But because of failures of equipment, and we don't really understand why this happened, in every case, rather than releasing it to the environment, they actually released it to that gray thing up above there, which we call the reactor building, which is outside it. So these radioactive gases and hydrogen went to the reactor building rather than out to the environment. And we don't understand why that is to this day. There are some failures or other that we don't understand. In any event, hydrogen and radioactive gases, and the radioactive gases amount to a few percent of all the radioactivity in the core, the rest of it is down in the rubble, went there, and one after another, all of those things exploded. Well, not all but one of them. The first one that exploded was Unit 1, where the hydrogen had some ignition source, not quite sure what. Could have been a battery, could have been, who knows. But the hydrogen exploded, and you saw the picture, it blew the roof off. I'll show you a picture of that in a minute. In Unit 2, the pressure in this building actually blew a hole out the side of the building, about the size of one of these windows. And the hydrogen was relieved in Unit 2, and it didn't blow the roof off the building. But in Unit 3, again, hours later, it blew the roof off the building. And so 1 and 3, the roof was blown off the building. And that released all those gases, and that was the radioactive release that contaminated the countryside. Okay? Just so you know what the source of that was. Had this vented stack worked, they could have perhaps relieved the pressure and the hydrogen, and it would have gone out, and and they would have not had this big explosion that then caused all that havoc. Now, the route for the gaseous release I've just described, but there was also a large liquid release. And this puzzles us because it shouldn't have happened by design. We don't understand it. I mean, the community that I'm in doesn't understand it. Let me describe it. This is all designed to keep the water in the vessel. And if not in the vessel, in the containment building. But for a reason we don't understand, This is a research pump line. In normal operation, there's a pump here that just circulates water to keep things stirred up so it doesn't stratify thermally in normal operation. And there are very large flanges here. They're about almost a meter in diameter. One there, one there, one there, one there. And as best we can tell, because there's no other way to explain this, those flanges failed, and water leaked out of the primary into the containment building, and ultimately water went into the as you probably read in the paper, water went into the turbine building next door, and then it went from there to a trench, and from there to the sea, and there was a lot of radioactive water that was released to the sea, amounting to 1% or 2% of all the radioactivity in the reactor. 1% or 2%. It wasn't, 100%, but it was what it was, and it was pretty nasty. And it also contaminated all the buildings and the grounds all around, which made it very hard for workers to go and try to figure out what was working and what wasn't. And all of that liquid release came out of those things that we don't think should have done that. Our designs, we believe, wouldn't have done that. We don't understand their designs. They don't either. They can't inspect it yet. Only later are we, the community together, going to find out whether there was something faulty in the design or the installation or the maintenance or we don't know what, and figure out whether there's something there to fix, because that thing is supposed to have been bottled up. So that's where the liquid releases came, and that's where the gaseous releases came. But I want to emphasize something to you about the size of this release. For the 3 reactors together, the total of all the releases was a little more than 5% of all the reactivity in the core. And one of them was 6%, another one was 4%, in that range. And just to put that in context, the large release at Chernobyl in the Ukraine released way over 90% of all the reactivity went out. And not only that, it went, as you perhaps remember, and if you don't, I can tell you, it was 1986. It was blown out the building, there was no containment, went to the stratosphere and spread all over, and as you probably know, there was serious contamination for dozens of miles and serious contamination out to 102 miles, and of course, less, but went all over Europe. And that airborne stuff amounted to 90% of the radioactivity. The total release here from these 3 units together was about 5% of what it was left. The rest is still inside those vessels, which is where we want it to be. And for a month or 2 after this accident, there was a struggle to try to make sure that water and all sorts of things got in there, jury rig and so on, in order to keep the core, it was now a rubble bed, underwater. Okay? Now, as perhaps you know, and if you don't, I'll try to explain, as the water level was going down, they have on-site tanks, but the piping to move from the tanks to the reactor didn't work because it didn't have any power. They had what you and I would call city water. It just came from the municipal water. It's a backup, very big pipes. They were destroyed by the earthquake. They tried to bring in tanker trucks right away with water. They couldn't get down the roads. The roads were totally destroyed. It took a couple days for that. In desperation, after the core started to melt, they injected seawater from an on-site fire truck and a hose to the ocean and injected, just jury rigged, but it worked. They injected seawater into each of those vessels, raised the level up, and saved the day compared to if they hadn't done that, because there would have been more degradation, more release, and so on. They got seawater in there. Later on, they had to clean the seawater out of there, but at least that's what they did. Now, having done that, things were stable, and they remained that way. Ultimately, fresh water has been replacing the seawater, and they remain stable to this day. Let me just go on. Seawater injection using a fire pump. Here's a picture, a sky picture of these 4 units. See the hole in Unit 2 that saved it from having been blown off? That's about the size of a meter or so on the side. Unit 1, the lid was blown off for what I said. Unit 2 was blown off. No, Unit 3, it was blown off. At first, we thought that Unit 4, everybody, the Japanese thought that Unit 4, the lid was blown off because, remember, all the fuel's in the spent fuel pool. We thought the spent fuel pool had lost level. They couldn't replace it. They didn't have pumping. And that it, too, evolved hydrogen, blew the lid off. A month later, inspections of that pool finally got in there, showed that that wasn't so. The pool's intact. No hydrogen came from that pool. This is a surprise to us. That was our interpretation for a month. The only interpretation we can think of is that hydrogen from Unit 3 went across a stack, this is a stack, but across a stack line over here, collected, and blew the roof off. And that the hydrogen explosion in Unit 4 was actually hydrogen from Unit 3. When you think about that, it seems very, very unlikely. I actually did some engineering calculations about reliability. It looks really unlikely. There are check valves in the way. They're robust. several of them. Doesn't make sense to us. But Sherlock Holmes once said that if you ruled out the impossible, the really unlikely is it. And we're stuck with not really knowing until later on some forensic work is done. But that looks like the source of that explosion in Unit 4. It wasn't the spent fuel pool. They were all intact. Nice to know. Let me keep going. And there's a picture. There's a picture of a vent stack. And over there you can see where the pipe is broken. But that break occurred after the explosion. And there's that pipe that goes across that is probably the source of that very light. Now, these are big buildings, as I showed you. Well, there's another picture I can leave. Fresh water. We brought in, the U.S. Navy brought in fresh water to provide a source of fresh water for them before they actually were able to bring in enough on their own. This is a barge doing that. And I'll leave that. I'm going to go back to some lessons. I'm just going to go back to this picture, and I'm going to talk about a couple lessons. The Japanese, besides not having put it there, had one other really important critical failing, and we knew about it in the first few days, but no one outside of Japan said anything about it in public for 2 months. And the reason is because saying about it would embarrass them, if you don't mind my saying, just being candid, and we wanted them to own up to it on their own, which they finally did about a week ago, and now here I am able to talk about it to you. They had a serious problem of decision-making in this reactor, which exacerbated this accident. It was starting. They were in trouble. But let me talk about control for a moment. Everybody in this room knows that if you get in trouble in an airplane, the pilot can do whatever is necessary to save that plane on his own, on her own. They ask advice. We want them to do that. They get analysis if there's time, but the pilot is in charge. In our reactors, the crew chief in the control room can do whatever is necessary to save the reactor. Okay? Not in Japan. If there are procedures, they can do it. If they're outside of procedures, they have to ask permission. And this happened twice for them, and this is a very serious problem which exacerbated their accident, which, as I said, we in the West can finally talk about because they've owned up to it. The first was, let me try to get this in the right order. The first was when they wanted to vent the Taurus, and this was a vent that was going to go outside, remember? By the way, it didn't work. It went to the reactor building, but they were going to vent outside, and that was going to release radioactivity to the environment, little bits, but it was intended to save the pressure, keep the pressure down in this building. Outside of procedures, they couldn't do it. They had to ask permission. They asked permission of the headquarters of Tokyo Electric Power in Tokyo. After 4 hours, they decided they didn't want to do it without asking the government. They asked the government. 3 more hours, they actually had a meeting in the Prime Minister's offices, I understand. It sounds nuts. I mean, anyway, 7 hours later, they finally gave them permission, and they did it, and of course, it didn't work. But the decision-making really was a problem there. And then, a day later, they wanted to inject seawater into the reactors, and I want to tell you that seawater injection will ruin the reactor. It's a $1 billion loss, although what they faced was much worse. So, again, asked permission to inject seawater. It took many hours of getting permission, during which time they didn't inject seawater, and things got much worse than they would have. They could have stopped a whole lot, although it was starting to get in serious trouble. It would have been better had they not had permission. Well, in one of the units, the control room chief took the law into his own hands. He risked his life, his career, his pension, and everything about him, and decided to defy their orders and inject seawater anyway, a couple hours before he got permission, thereby saving serious damage, although they had serious damage, saving at least worse damage in at least one of those reactors, because their decision-making process doesn't allow the person in the control room to make those decisions. And they have now owned up to this, and they say they're going to change that. It's part of the way they went about reactor safety wasn't really appropriate. And it's a serious institutional problem. I'm not sure whether it's Japanese culture or the way that, anyway, without arguing about the details, those exacerbated the accident, but in fact there were really 2 technical causes of this accident, which I already described. The first is they should have never put it there unless they had a bigger tsunami wall, but you saw all along the coast, 26,000 people paid with their lives because they didn't put up one, so they somehow missed that, and it's a very serious indictment. And the second thing is, for reasons we don't understand, when they lost all AC power, those non-electric systems didn't run as long as they should have. We're not sure whether it's an engineering problem. We just don't know, and we're not going to know for a while, and they're not going to know for a while. And if it's an engineering problem, then maybe there's something that we all have to fix. Or maybe it's something specific to them. If it was only one, we'd say, well, it was one. But it was 3 of them. So it's got to be more systematic than that. And everybody that's running boiling water reactors, in fact, all of us around the world are looking very carefully at that to try to see if there's something that we need to do right away to fix our reactors. We don't think so, but we're not going to know for a while. Okay? Those are the fundamental causes of the accident, some mix of engineering and so on. And then this institutional problem of decision-making, which didn't enable the control room to do what they had to do until they waited a long time, and things got worse while they waited a long time. Something that is surely not correct. Okay? Let me go down. I was going through this. There's that freshwater barge and so on. So now let's talk about the U.S. just for a minute. This is a map of the U.S. sort of stylized. We have 104 reactors. There are 23 of them that are Mark I boiling water reactors designed by General Electric. They're basically identical to these, different sizes, but they're more or less identical to the 6 there. And this is just a map that shows ages of them and so on. And they're scattered around the country. There are no BWRs in California, but they're scattered around. And all of them are now carefully looking at all these things as you imagine, as, by the way, all of the pressurized water reactors are looking at some of the other lessons learned. And the future of this whole program is totally unpredictable at the moment. These reactors are all running. They're all licensed for 40 years. 2/3 of them have already received a 20-year extension from 40 years to 60 years, a 60-year license rather than 40. The others are going through the process. Nobody thought that 60 years would be a problem. But these, absent this, these are going to run out to 60 years. Some of them are 30 or 40 years old already. Some of them are only 20 years old. There are no young ones. The youngest of them are 20 years old. And so this program is underway. There hasn't been a new reactor, as probably a lot of you know, in the United States for more than 2 decades. But in the last 2 or 3 years, a whole bunch of utilities have been applying to the Nuclear Regulatory Commission to build some new design reactors. There are actually 24 or so in the application process at the Nuclear Regulatory Commission. They're mostly in the southeast, but some elsewhere. And they're going through the process. They're using much more modern designs than our old reactors. That doesn't mean the old ones aren't generally safe, but newer in the same sense that a brand new airplane like the 7X7 is so much safer than the 747 or the 727 that preceded it, because modern electronics and modern control systems and modern this and modern that, modern welding, modern materials, everything is better because, of course, time passes and technology improves. Whether those 24 or so are going to proceed, God only knows. Right now they are. Nobody's abandoned it yet. It's really hard to know. I can't predict the weather next week, and I sure can't predict that. And I don't know anybody in the business I'm in that's willing to take a gander, including people who are running these utilities, who are applying for these plants. There's still a whole lot of lessons to be learned that we haven't learned yet. We may find that there's a fatal flaw in these BWRs. And if that's true, the NRC will shut them down. And, okay, we may find that it isn't. Well, we'll see. That's still to come. One last thing, and now I'm going to talk about radioactivity and show you where the doses were, and then I'll just time for questions. Perhaps you know about radioactivity in the United States. The average American gets about 200 or sometimes 300 millirem per year from natural background sources, a lot of it from rocks and soil and radon, and some from the food we eat and cosmic rays and so on. And perhaps you know that if you move from Berkeley to Denver, we have a granddaughter that lived in Boulder for a while, they get another couple hundred. They get almost twice as much up there because there's more in the rocks and there's more cosmic stuff. And then on top of that, in the United States, everybody on average, we don't all get it, but on average, there's a comparable amount from medical. Some people get a lot, some people don't get any. On average, it's a comparable amount. It adds up to about 600. And as I said, in Denver, it's another 200 or 300. And I want you to keep this in mind, this 300 of natural and another 300 of medical when I talk about what happened in Japan. Because that's the context of the background we get every day that people always got, plus the medical that we get now. And now I'm going to show you what happened in Japan. This is my last slide. This is a picture of the site. And I just pulled it off the web just to show you a typical sort of picture of the plume. And there are 3 circles there. The inner circle around the site is 20 kilometers. That's 12 miles. The next circle is 30 kilometers. That's just short. That's 18, 19 miles. And then the final circle is 80 kilometers, about 50 miles. Just to give you a scale. Now, the day that all those releases took place, the day and a half, the wind was blowing to the northwest. And you can see the plume going up there. And there's an area there that goes out about 20 miles. It's the sort of yellowish and orangish area there. I mean, this isn't exactly right, but this is sort of the schematic. And it's 2 or 3 miles wide. And that area is where the principal contamination went. And that area, they evacuated the whole circle out to 20, and in that region 30 at first, kilometers. And they're still evacuated. But that's the area where the contamination is, and they're just about to let the other people reoccupy. But in the area where they're going to maintain their evacuation, and perhaps they're going to have to do much more, they chose the criterion that if in a year a person living there got 2,000 millirem or more, that was the criterion. Above that, evacuate. We're going to try to decide what to do, clean it up or raise the buildings. They're still working out what to do. And anybody that gets less than that, you can reoccupy. And by the way, people are going to take some prudent measures. People can make local measurements because sometimes it's more in your house than it is in the community. But that area has something like 40,000 people who, by the way, in the first 2 or 3 miles it was destroyed by the tsunami. But outside that, the houses are fine, but they can't reoccupy them because of radioactivity. And those people are going to be out of house and home, those 40-odd thousand, for the longest time. It's going to be a year, it might be 2 years. They're still trying to figure out whether they can clean up some of it. Maybe they can't, maybe they have to raise it, maybe they have to strip off soil. There's a whole lot of work that's going on right now to try to make those decisions. But in the meantime, you can see that the area of concern is pretty big. I mean, it goes out 20 miles, and it's 3 or 4 miles wide, roughly, and I just pulled this off to show you. The rest of it is lower, and almost nothing went south. And Tokyo was fine. There was nothing there where all the millions of people live, but I'm sure some, at least in between. By the way, these blue lines are just flight patterns of a plane that day. I just pulled this off the web to show you the rough map. Now, what's going to happen here? They don't know, and for sure we don't know. It could be that they will find that cleaning up those houses is feasible, in which case a lot of money will be spent, and they will. It could be that for some of them they just can't. They're going to have to take them down and bury it. That's not known yet, just because there's a lot of measurements to make, and there's only so much in the way of resources, and a lot of analysis to do after the measurements are made. So I'll leave you with that idea that there were about 40,000 people. Now, the financial impact is as follows. The estimate of the cleanup of this area so as to make it livable again is thought to be in the range of 20, 30, or 40 billion dollars. They don't really know. That's a big range, but 20, 30, 40 billion. It's a lot of money. The cleaning up the reactors is going to cost 10 or 20 billion. They're going to wait a couple of years and take them apart and bury all that stuff, just like what we did at 3 Mile Island. By the way, at 3 Mile Island, remember I said a few percent came out of here, and at Chernobyl it was 90%? At 3 Mile Island, it was about 10 to the minus 4 of all the radioactivity came out, even less than 10 to the minus 4. So there was almost no release at 3 Mile Island in 1979 compared to this, just as a context. Now, let's put this in context. The tsunami killed 26,000 people. The people that had to evacuate and lose their homes, never minding the businesses, were 400,000 from the tsunami, right? 400,000. And you've seen the pickups of the pictures. Recovering from that is estimated to be 500 to 700 or even 800 billion. So it's 5, 7, 800 billion from the tsunami, 20, 30, 40 billion from this, 10 or 20 billion to clean up the reactor. The reactor is big and messy and huge, but it pales in the total economic impact to the other. And of course, there's also a whole lot of work to try to understand the contamination in fish from the water that went to the sea, and contamination in the milk and in foods and water and stuff like that. And of course, as you probably understand, the Japanese are excellent at being rigorous and disciplined about interdicting everything, so no one's drinking anything that's radioactive, and that's at least a disciplined, confident process, but the economic impacts are just very, very large. I'll leave you with just that last slide. I'll leave it up and close just with one quick thought. Every single one of our reactors is right now in a 30-day period of trying to evaluate the 10 or so things that went wrong here and see whether we're susceptible. I know I was at Diablo Canyon just this week. They're at the end of their 30-day period. They're writing their reports. They actually didn't see anything that mattered much to them. That was a lesson learned here. All the stuff that happened here looks like they're already robust against. So the offsite power, they're high and dry for the tsunami, a whole lot of things. So that's nice to know. Until we get all those reports, we won't know whether or not others have identified some things. We're all going to know in another week or two. And people like me are going to be looking at it because there's a lot to learn from one reactor to another. Somebody finds something, everybody's going to go and see whether, in fact, they overlooked it. There's going to be an iterative process. This is not just going on here. There are 400 reactors around the world, and everybody's doing this right now in parallel as we have finally learned some of these lessons. And I can tell you that it's probably going to be another few months before other lessons are learned because they're going in there. For the first time they have access, they're going to look at some stuff. And they're going to see what failed and why, and see whether or not some things that we were supposing are so, or maybe not, or maybe something new. So it's going to be a while before all the engineering insights are available to them and later to the rest of the world. And so it's going to be some time before, I wouldn't be surprised if it was a year or two, before all of that's assimilated and before we know how serious our problems are, if any, in all of our different reactors. Some of them are going to have some of them maybe not. I don't know, I have an open mind. We'll just see how it plays. Finally, you know, if you're a nuclear reactor engineer, this is the horror show of the century. And you probably understand. When the Chernobyl accident happened, I said, well, it's the Soviets. And it was true. I mean, it's awful. But these aren't Soviets, these are Japanese. Well, it was Soviets. These are GE designed reactors. These are like ours. So it's a real comeuppance of the most serious kind. On the other hand, it's an exciting time. In a macabre way. It's an exciting time. And there's a whole lot of stuff here. I've spent a life, and I'm not the only one, thinking about these things. And now we've got real stuff to think through that is going to affect the future of the whole world's nuclear program, which, by the way, almost 20% of the world's electricity around the world is generated by nuclear power, and so it's not a trivial thing. And how it plays out, darned if I know. I'm not the only one that's going to say that. So thanks a lot, and I'm happy to take questions, and I'm walking out the door at noon. Okay? And I said I'm walking out the door at noon. Yes. Actually, the roads were blocked for a couple days, all right? And then wait a minute. And then when they brought them in, they have hookup panels for just this contingency, and they were all wrecked by the tsunami. So they had to bring them in, and that took a week. All right? Okay? It was really just a great tragedy. Steve?
Yeah, it seems that the major threat to U.S. reactors is not from a tsunami, but a Category 5 tornado.
Yes?
Instead of having a 100-foot wall of water, you've got 200-mile-an-hour surface winds and the destruction of the grid around it.
Nicely spoken. Our reactors are all in a place where that on-site power we think is protected against that. All right? Now, everybody's looking to make sure that there isn't some vulnerability that they overlooked. But we have protection against that, and that's a nice thing to say. Remember, the threat isn't the tsunami. The threat is the blackout, however you get there. After 9/11, all of our reactors, in a program that wasn't widely publicized because you know why, went around and made sure that no single attack like that could disable all of the on-site electric power by separation and the like. Okay? And some changes were made in our reactors to make sure that they were robust against, I mean, you have to imagine an airplane, or it might be some other device, or an inside job, that no one thing like that could disable everything in our reactor. So we already have the separation. They did too, but the tsunami got it all. Okay? It's just... Okay. Yeah. Go ahead, yeah. Yeah. They did. Yes, they couldn't bring it in. All right, they couldn't bring it in for a couple days, and then finally they did. And when they got it in, they found that the distribution system to distribute the power had all been destroyed by the tsunami. Oh yeah. Well, no one had designed anything like that in which all that steam, the steam dump just ran a small pump. That's the way the design is. That's a possible thing that they could all install. Yeah. Oh no. Absolutely. No, well, it wasn't overblown. It was erroneous, and that's different. We all thought that the explosion in Unit 4 was because the spent fuel pool, remember, there's nothing in the reactor. It was all in the spent fuel pool, but it was freshly discharged. The level had dropped because they couldn't replace the water. They had had oxidation, and the hydrogen blew the top off. And now we know that wasn't so. Now we know that all of the spent fuel pools are intact, that no damage to any of them caused any trouble to anybody. But for a month or even more, that was a big concern on our part because we said, gee, maybe the calculations we do or something about it, that there was a big concern for spent fuel pool integrity. We now know the spent fuel pools all had seismic integrity. By the way, there were four units just a few miles down the coast being inspected. They didn't have any trouble. Everything was fine. They had the same ground motion. Okay? So overblown isn't fair. It was an erroneous conservative judgment based on what was known at the time, which was then later learned not to be so. Okay.
Yes, you don't hear much about this in the news today, and I was just kind of curious as to today in terms of heat removal and where the reactors are at.
Okay.
Is there still a process?
Yes. 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 It's going to be a year before the heat will go down enough for them to get in there and start taking it apart. They finally brought in specialized equipment, brought in from offsite. And in every one of the units, there's fresh water going in, there's steam going out, it's being condensed, there's a regular cycle going in. Now, at first, that was all jury-rigged equipment. And jury-rigged equipment is notoriously unreliable. Anybody that's ever done that knows that. So after about 2 weeks of jury-rigged that, and some hard work that was actually done here at Brookhaven, colleagues, dear friends and colleagues of mine at Brookhaven did the design. A design for a much more reliable system was arrived at and fabricated over 2 days at Brookhaven and flown over there. And that stuff, with some Japanese now enhancing it too, is now providing reliable water supply for those reactors, water circulation and supply and control systems and the like. And now the Japanese have brought in another system to back that up, so in case there's a failure, there's something right next to it. So we think those systems are now going to be stable for the longest while. By the way, they were also been designed for aftershocks. And let me describe something to you. This is the Earth Sciences Division. Some of you know this. I'm not an earth scientist. When you have a 9, aftershocks are 7.5s, and 7.5s are big earthquakes. And they don't just occur on the feature that happened. They can occur around Japan. And in fact, they've had aftershocks hundreds of miles from the original source. And so they might have they could have a 7.5, which would be real trouble. These auxiliary systems have been designed for that, on isolators and the like, with some care. So we have confidence now, finally, that we don't think they're going to get in trouble now with keeping the water over that rubble bed, and therefore getting any more core recovery and more releases. Now, you never know. The rubble bed is at the bottom of the vessel. There are penetrations down there for control rod drives that might leak through. Just the other day, the Japanese announced they thought that some of the core in one of those units had leaked out of the vessel through some of those control rod drive channels to outside below. But that's unconfirmed, and later on some other people said it wasn't. But in any event, it's still inside that containment. We generally think that it's going to be stable now. And we're hoping, of course, that we don't get caught by surprise again. Hold on.
The possibility of not grid criticality?
Oh, yes. There's no criticality problem at all. The rods went in. Okay, chain reaction was shut down. The rubble bed is way less of a critical configuration than the other configuration. You just can't get criticality from that. But besides, the water that's in there is borated. The steel structures that are all melted in there are borated steel. Whatever it is, we're not worried about criticality. We weren't from the moment the rods went in until now. That's not a concern. There's way more margin for that than you'd have to worry about. Okay? You had a question? Oh, it's the same question. Margaret? Well, there's going to be a huge decision point depending on whether we find out that hardly any safety factors are necessary for our reactors or some big ones are. Not just because of cost or But because that'll, as it should, will change people's perception of whether the designs have been competent all along. We don't know that yet. I just spent 2 days at Diablo Canyon, and they had 30 things that they looked at, and there wasn't any of them that looked like there was any change in this meeting. Now, that's nice to know, all right? I mean, by the way, people are going to review it, I'm going to review it. But the first look doesn't seem to show that. And if that's true, that's a qualitatively different situation than the opposite, and we're not going to know for a while. Okay? And it's particularly true with the boiling water reactors, which are like this. The pressurized water reactors have so many features that are similar, but so many that are different, that only some of the lessons are applicable, and others. But of course, by the way, if this could happen here, what do we know about ours that we don't know? Well, this is a comeuppance. I got to tell you, it's a very difficult situation, and we're all trying to think it through together. Larry. Yeah. Yeah. Well, there are two things here. The first is the earthquake hazard. They actually designed for that very big event. It was remember, it's the biggest earthquake they'd had in 2,000 years. They designed for it. The design basis and the size of that were comparable, and they had plenty of margin, and it all did fine. So that's comforting. On the other hazards, there's a real question about whether not just the frequency, say, of tornadoes, but their size. Because, if the frequency of tornadoes in Kansas becomes 3 times more frequent than before, it doesn't change anything. There's a reactor in Kansas. It better be designed for it, and it is. But if the size is different, why, that's different. Same thing for tsunamis. They were, obviously, 26,000 people paid with their lives because you saw it, the whole coast didn't have enough. The tsunami experts, and I attended a talk by one recently, were humble and candid about how they really didn't know as much about predicting these things as they wished, and they don't know any more now. That tells you something about, you don't design for the thing, you put it somewhere else. Bob Budnitz's solution, you put it somewhere else. The one down the coast survived because it was high enough. It had the same tsunami, it was high enough. It seems to me that trying to put a fine point on these design questions is not an adequate solution for me. Especially, with warming and sea level rise and big storms. You remember, a tsunami that comes when there's a storm surge is higher than one that isn't. They didn't happen to have it here, but it could have. And, the combination of a high tide, which is another couple meters, and a storm surge is another couple meters, things get bad that might not otherwise. So it seems to me that the crucial thing for tsunamis is sighting. And for tornadoes in the middle of the country, you can't sight against them. They're everywhere in the middle of the country. The NRC's design criteria for tornadoes are thought to be strong enough to withstand bigger than has happened. Okay? I've actually gone through the engineering of the containment structures there, and I think it's so. So we don't think we're going to be surprised by tornadoes. The place where we might be surprised, if you don't mind my saying, we might be surprised by earthquakes in the east. Not here, but in the east. Reactors in the east are designed for much less earthquake motion than here, but there have been large earthquakes in the east, a few. They've been designed for them, but what if it was even bigger? Probably some of you may know that was it 1811, just 200 years ago, there was a huge earthquake in southeastern Missouri, and it rang church bells in Boston and in New Orleans. It destroyed everything in the county, but of course there wasn't anything in the county in 1811. And in Charleston in 1886, there was an earthquake that destroyed the whole of Charleston. It was very localized. It didn't destroy even the suburbs. The reactors in those areas are designed for those motions. Could a 9 come along where the previous biggest one was a 6.5? I'm not a seismologist, Larry, you are. So there's this question about how far you push this, and as I probably guess, the community of seismic people in the reactor business is thinking about that hard. I was at a meeting the last 2 days of last week, just Thursday and Friday last week, in which we were talking about just that very question. I'm on the engineering side. These are the seismic people. And there's a reevaluation going on, and first trying to figure out how much margin we have against the big motions. You know, you design for something, but it can withstand more, but then how much more? And with what confidence? And also, whether there are some easy things to do that can make a big difference. And in some cases there are, in some cases, of course, there aren't. It's a lot easier to anchor equipment than it is to build a new structure. You know, that sort of thing. Oh, Herb.
What problems, if any, are associated with the removal? What do you do with
Oh, well, we have one data point at 3 Mile Island. Now, at Chernobyl, they buried it. Okay, so we don't know. At 3 Mile Island, it was all taken apart. It started 4 years later. It took 2 years. It was done 1 kilo at a time, all right, with remote, okay? And by the way, all that core is buried in a vault in Idaho National Laboratory. If you don't know that, I can tell you where to go. And where it's been for 25 years. There is technology to do it. There's remote handling equipment. It's messy, it's expensive, and it takes a long time, and you have to be really careful because even though a little bit of that stuff is hotter than a pistol if you get near it. But that's known technology. What's to become of it? Well, the stuff at Idaho is sitting there in this vault waiting for a repository someday. If it isn't Yucca Mountain, it'll be 30 years from some other place. And presumably that's the same thing there. They have actually already begun a team to look at that and are using the experience and even some of the people from the 3 Mile Island, Idaho crowd from the early 80s. Okay? That's messy but doable.
So it seems like from your previous slide that the radiation amounts have very little health effects.
Oh, you have to be careful. 2,000 millirem per year over a bunch of years brings with it a small, but at least nominally understood, probability that it might bring cancer to a subset of those, statistical subset of those people. Is 2,000 the right criterion per year? No, I remember, if they reoccupied, it might take a few years. Is it 1,000? Is it 5,000? The Japanese have made that decision based on some risks and costs and so on. But it wouldn't be fair to say that just saying, oh, 2,000 isn't much. Remember, you're talking not about a few people, but about 40-odd thousand of them. If you multiply that out, statistically, you can work out based on, you know, our understanding and their conservative assumptions about the linear hypothesis, and Tom McCone sitting on my left here knows way more about that than I do, and some of these things aren't known at these, 2,000 is still a low dose compared to where things are really known, but it wouldn't be fair to say that reoccupying that wouldn't produce those effects. In a single individual, the probability is low. You put 10,000 of them in there, some of them are going to find something perhaps 30 years later, and you can work out the statistics. And of course, it's particularly bad for, you know, fetal exposure. And so they're making their risk and political decision on their own. But 2,000 is not just being ridiculously conservative. Oh boy! Oh boy! Yes. Yes. Yes, and there's a treatment plan going on right now. Correct. They, over the last month, using American equipment and some of theirs and some from Europe that was donated and assembled, they assembled their first of what is going to be several of these treatment plants where radioactive water go through an ion exchange, you concentrate the radioactivity, the water then can be reused or discharged. And they got it up and running, and 3 days later they concluded that it wasn't doing what it was supposed to. They're working on that now. They need a decontamination factor of about 1 million for it to be clean enough for discharge, and they were only getting around 10 to the 4th, and so they're struggling. I was actually on the phone yesterday for half an hour with some people about that. Not that I know anything about that, I'm not a chemist, but I knew a couple people that I happen to know that I could recommend might help that they haven't thought of. So is that going to go well? There are going to be these troubles. Is there a rush? Well, there's not a rush on the order of days, but they're accumulating radioactive water as we go. We've sent in, you saw that Barb's picture I showed? We sent in several of those, and there's actually a huge balloon the size of a football field and 20 feet high that's filled with water, and we're bringing in another one. All that's American. All that's going to have to be cleaned up pretty soon. Okay? No one's going to discharge it, you know, to the environment. No, wait, I've got one back here.
So I was wondering, do you have a corresponding map showing the radiation level in the ocean?
no, I don't have it. I don't have it, but it's actually quite small. The problem in the ocean will be concentration in the biota that ultimately ends up at the top of the food chain. But that takes time. So that if you discharge something on day one, the fish aren't radioactive on day two. It goes through a food chain. So I'm not an expert here, but it's my understanding that it's going to be some time before the top of the food chain, the stuff we eat, is going to show this stuff, and they're monitoring it as they should, and biologists are trying to do what they're trying to do. The contamination in the sea goes out a few kilometers. There's dilution after that. And of course, you know, there was sedimentation in the near shore, which produces concentrations that are more troublesome than if it was all diluted. You can find it on the web, and I probably have it somewhere, but I didn't bring it along. Okay. Yeah, one more.
The tsunami in the Indian Ocean about 10 years ago.
Well, it was the end of 2004. Go ahead. Yeah.
As far as I know, at a height in Thailand that exceeded the height of the Tsunami Wall at the Japanese point.
Oh yeah, they had a particular run-up situation there in a shape of the beach that caused a very, very large tsunami, even though it was hundreds of kilometers from the
Yeah. The question is, if you were in the Japanese nuclear industry, you didn't notice that just 7 years ago, there was a tsunami that would have topped the wall.
Well, to be fair, and I'm not going to give you a value judgment. I'm going to tell you what they did. They had concluded that feature where that earthquake would produce a tsunami that was 5 to 6 meters. Okay, so they built a 7-meter wall. Okay, they thought that was enough. And you know, you got 1 meter over isn't a trouble. They didn't get 7 meters; they got 14 meters. Went right over. It wasn't as if they hadn't thought of it. They missed it. Now, the wall, as you saw ahead of the slide, was different in different places because there are different local conditions. They tried to account for that. Walls were higher or lower. They tried to account for it. They just missed it. I'm not. This is just descriptive. I'm not trying to blame. You know, I mean, obviously somebody's feeling bad, and they should. But they went back to the tsunami. Explicitly, they went back to that tsunami in Sumatra, and it went to Thailand and wherever it did. And they did analysis of that to see whether or not their prediction for the thing that they had was accurate, and they found that it was okay. It's just that that earthquake was bigger. I mean, all right, the drop was bigger and the wave was bigger. Okay? Any others? Well, I do get out at noon. Thanks. By the way, you're going to laugh. You know where I live right near the circle? Yeah. Well, I've got they won't pick me up at 12:45, so I got to get home because I have a 3 o'clock flight. How are you?
I'm just fine.
I'm sorry. That day when I missed you, I was actually out of town.
All right.
I wanted to go to that final session because it was going to be in there. Yeah. No, it's actually 7:17. Yes. Yeah.
Bob, thanks very much.
Of course, it's a pleasure.
Wonderful.
I see you every so often. Nice.
What